When we talk about estimating, the subject covers a wide area. For example, we could be talking about estimating the height or length of something, or we could be estimating how long something takes. Now, we have been looking at rounding, and we're going to be using rounding to make estimations of calculations. So in this video, we are going to estimate the value of a calculation by rounding the numbers in that calculation to one significant figure. We're also going to look at the size of the error and calculate that error as a percentage of the actual value. You're going to need to be comfortable with calculations involving multiples of 10. And for some of the questions we are going to be looking at, you will need to be familiar with order of operations, or BODMAS. Now, I have covered these topics in previous videos, and the links are in the description below. So for this video, I'm just going to look at 6 examples. As I go through, feel free to pause the video at any time and have a go yourself. So question 1 is 37 multiplied by 24. So what we're going to do is we're going to round 37 and 24 to one significant figure. What we do is we put in these 2 squiggly lines to say that this is an approximation. 37 is 40 to one significant figure, and 24 is 20 to one significant figure. And 40 multiplied by 20, well, 2 4s are 8, add the 2 noughts, gives us 800. So there is an approximation to 37 multiplied by 24. We're going to look at the actual calculator answer later on to compare the actual answer with the estimation. And we will repeat that for all the questions shown here. Question 2, 8.73 multiplied by 21.7. So 8.73 becomes 9, and 21.7 we can write as 20. So 9 multiplied by 20 is something you should be able to do without a calculator, which is, well, 9 multiplied by 2 is 18, add the naught is 180. You might want to pause the video and have a go at the other questions on your own. I'm just going to continue going through each question using the same approach. Question 3, 48.2 divided by 15.9. We write 48.2 as 50 and 15.9 as 20. Now 50 divided by 20, the noughts cancel out. So we have 5 divided by 2, which is, of course, 2.5. Question 4, 27.4 multiplied by 2 divided by 13. 27.4 will become 30 to one significant figure multiplied by 2, all over 10. So we end up with 60 divided by 10, which is, of course, equal to 6. Question 5. So here's a bit of order of operations. 23 multiplied by open bracket 14.1 subtract 9.2. So I'm going to write 23 as 20 to one significant figure. But for 14.1, I'm going to write that as 14 and then subtract 9, because 14 subtract 9 is a nice easy calculation. So we end up with 20 multiplied by, well, 14 subtract 9 is 5. So we end up with 20 multiplied by 5, which is equal to 100. And finally, we have 191 add 21.74, all multiplied by 1005. Remember, the whole idea is to make the calculations easy. 191 I'm going to round to 200. 21.74 I'll round to 20. And then I'm going to multiply all of that by 1,000. So we have 200 add 20, which is 220, multiplied by 1,000 is going to give me 220,000. So notice that in these last 2 questions, question 5 and question 6, when it came to rounding the numbers in brackets, in question 5, I just rounded to the nearest whole number because 14 subtract 9 is not a difficult calculation to do in my head. But in question 6, I rounded 191 and 21.74 to one significant figure, just to make the calculations easier. I'm just going to show the calculator answers. And what we're going to do is compare the calculator answer to the estimate. I'm going to look at question 2 and question 4, and what I do for those two questions, I want you to repeat for questions 1, 3, 5 and 6. If we look at question 2 as an example, so we have an estimate of 180 and the actual answer is 189.441. So it looks like a pretty good estimate. Well, let's work out the error for this particular calculation. And the error is, of course, the rounded number subtract the actual value. So the error is 180 subtract 189.441, and that gives us the answer minus 9.441. Remember that this negative sign is telling us that our estimate is smaller than the actual value. Now let's look at the error for question 4. So we have our estimate of 6 and our calculator answer is 4.215 to 3 decimal places. So our error is 6 subtract 4.215, which is equal to 1.785. And this, of course, is positive because the estimate is larger than the actual value. Now you would think, because the size of the error in question 4 is smaller than the size of the error in question 2, that the estimate in question 4 is a better estimate for that particular calculation. But what we're going to do for each question is compare the error to the actual answer as a percentage, and then compare the errors of both questions using those percentages. Now we have covered comparing values as a percentage in a previous video, and I'll put a link in the description below just to remind you. So we have an error of minus 9.441. Well, how does this compare to the actual calculation? So what I'm going to do is put into the calculator 9.441 divided by 189.441 multiplied by 100. Notice that I haven't included the negative sign. This is because we're only interested in the size of the value, the 9.441. Remember, the negative sign is just telling us that our estimate is smaller than the actual value. We end up with the answer 4.98% to 2 decimal places. Let's repeat the process for question 4. So we have our error, 1.785. We'll divide this by 4.215, then multiply by 100. And we get the answer, 42.35 to 2 decimal places. So now if we are comparing the percentages, the error as a percentage of the actual calculation in question 2 was 4.98%, whereas in question 4, the error as a percentage of the actual value is 42.35%. So looking at those two percentages, which would you suggest is the better estimate? So this would suggest that the estimate for question 2 is a better estimate because the error as a percentage of the actual value is smaller than that in question 4. What I'd like you to do is to pause the video and then for the remaining questions, so that's questions 1, 3, 5 and 6, work out the error in each case, so that is the estimate subtract the actual calculator answer, and then work out the error as a percentage of the actual calculation and give that answer to 2 decimal places where necessary. So pause the video and have a go. Here are the errors and here are the percentages. For question 1, the error was minus 88 because the estimate was smaller than the actual calculation, and we ended up with a percentage of 9.91. For question 3, the error was minus 0.531. Again, the estimate was smaller than the actual answer, and we got a percentage of 17.52. For question 5, we got an error of minus 12.7 and a percentage of 11.27. And finally, for question 6, we got an error of 6,196.3, which seems like quite a huge error. But when you work that error out as a percentage of the actual calculation, we ended up with a percentage of 2.90 to 2 decimal places, which would suggest that when comparing the errors to the actual answers as a percentage, question 6 provided the better estimate. So there's a brief look at estimating calculations by rounding the numbers primarily to one significant figure. In the next video, as promised, I'm going to be returning to errors and looking at writing the range of possible values from a given rounded value using inequalities. But I hope you found the video helpful, and thank you for watching.